Hey guys, this is the second video for chapter 12. And as you can hear from my voice, yes, I'm still losing my voice. So I apologize. Hopefully, again, there won't be too much of my voice cutting out on this. So in this section, we're going to talk about what correlational data actually looks like and how we do the statistical analysis for that. And this is going to correspond to learning objectives 2 and 3, which explains how correlational studies and correlations describe the direction, the form, and the strength of a relationship between two variables, and how to identify these in a data set and in a scatter plot, which we will talk about in a second. And then how to identify the statistical procedures that determine the correlations for the different types of data that you may have or that you may encounter. And keep in mind that most of the time, even if you're interested in the relationship between multiple variables, we usually, when we're talking correlations, it's usually you're looking at two at a time. So two variables at a time. So if you have multiple variables in your study, likely they will be paired into groups of two for evaluation, so that you can say, there's a relationship between these two variables, there's a relationship between these two variables, and then you may take a variable from each of those and say, and then this variable and this variable are related in this way. But you will likely talk about them two at a time, if that makes sense. So as far as evaluating these relationships, first we're going to talk about for numerical scores and ranks. So, because remember, data can be non-numerical. So this is all about the numerical scores. So in this case, scores are identified as X and Y. And when it's talking about pairs, it means every person gets measured twice, right? Because you're talking about two variables that we're interested in. And so your first variable would be variable X, and your second variable would be variable Y. Data can be presented in two different ways. It can be a list showing the two scores for each individual, so all the scores for both variables, or, well, and it can be both, and or scores can be shown in a scatter plot graph where each data point or single dot is coordinates with the with both variables to form one single point. So of course, verbally that is confusing, right? But visually that'll make a lot more sense. So here we go. Let's look at it. So on the left, you have the chart we were just talking about, a list. So we have the person or participant A, B, C, D, E. They're just labeled with a letter. So that's the participant. Variable X, there's the scores for variable X for each person, and then the last column is Y, and that is the variable Y, and you have the scores for each of that, for the variable for each person for that. And so on the right here is our scatter plot. You see our little dots. You see along the bottom, that line is called the x-axis, where it says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the x-axis, so that is for the variable x. And then on the vertical axis, this vertical line that says 2, 4, 6, 8, 10, 12, that's the y variable, that's the y-axis. And so you can see for person A, if you look at the list on the left, they scored a 1 and a 3, a 1 on variable x and a 3 on variable y. So if we go along the x-axis to 1, and then we go up the y-axis to 3, because they scored a 3 on the y variable, you see there's their data point, point A. That's person A. That's their data point. So it corresponds with both variables to form one singular data point. Okay, and you can follow that for B, C, D, and E to see how they got those points as well. But you see that's how a scatter plot works, and that's how they get that visual representation. So this is also figure 12.1 in your chapter, if you need to refer to that. So from here, once we've done this, typically researchers will then calculate a numerical value, which is considered a correlation or a correlation coefficient. It's the same thing. Sometimes people just say correlation. Sometimes they actually say correlation coefficient, because a coefficient is just that numerical representation of the correlation. Okay, so for a correlation coefficient, um, it is describing and measuring the relationship between two variables, which we've already discussed. There's three characteristics that that coefficient is going to shed light on or is going to describe, and it is the direction, the form, and the consistency or the strength of the relationship. So first, let's talk about direction. Um, so for direction, it can be positive or negative. Okay, we've talked about this a little bit already, but positive relationship means the two variables are moving in the same direction. As one variable increases, so does the other, or as one decreases, so does the other. They move together in the same direction. Negative relationship means they move in opposite directions. They still are moving together, they're moving at the same time, they're just moving in opposite directions of each other. So as one increases, the other decreases. Excuse me. Um, an example of a positive relationship would be height and weight. So generally speaking, as height increases, the weight of that person also increases. The taller they are, the more they weigh in general. Of course, there's exceptions to that, of course, but there is a relationship there, though, right? Like it's not what we're talking about is just that a relationship exists. It's not a perfect relationship, but it exists. The trend is that, generally speaking, as one increases, so does the other. An example of negative relationship would be um, your book uses the example of speed and accuracy. So, as in a performance-based task, a lot of times if they are going too quickly, they aren't as accurate. So, faster speed leads to lower accuracy. So, as speed increases, accuracy decreases. So, they are moving in opposite directions of each other. Another example, more real life example of negative relationship is um, hearing. Gosh, I couldn't think of the word. Hearing or eyesight um, and age. So as age increases, many times eyesight or hearing decrease, right? As a person gets older, their eyesight and their hearing may decrease. And so that is an example of a negative relationship there. Um, so if we go back to figure 12.1 really quickly, um, you'll see that this scatter plot here is an example of a positive relationship. And why do I say that? Because you can see as it's moving in an upward direction for one thing, but as the variables or as variable x values increase, so as you go across from 1 all the way to 10, you see that the scores on the y variable are also going up. So um, as the if you go as you go across from A to C to B to D to E as those persons, as you go across, they are increasing their X scores, but they are also increasing their Y scores. They're also going up as well as moving across. Okay, so when it does that, that is a um, positive relationship. It's moving up. If it was a negative relationship, the direction would be the opposite. So A and C would be up higher in the Y, on the y-axis, like they would be near 12. And then D and E would be down closer to 2. And so it would be switched. It would be going downhill. It would start up high on the left side and it would go down as it went to the right side. Again, because in that case, the higher y values would be associated with the lower x values. As x increased, y would decrease. And so that would lead to a negative relationship because as one increases, the other is decreasing. So another thing I wanted to point out, though, for direction is that this is the directional symbol with the coefficient, the actual value. So if it is a positive relationship, it will be a positive coefficient. So it will be a positive number. If it is a negative relationship, it will have a negative sign in front of the coefficient. So it would be a negative correlation coefficient. Notice that that is just a directional symbol. That positive or negative sign is just a directional symbol. It is not indicative of strength at all. We will talk about strength here in a second. That is different. That has nothing to do with this directional sign. The strength comes from the actual value of the number, which we will talk about in a second. So the second characteristic, though, before we get to strength, is form. So, sorry guys, I'm trying to clear my throat. The linear relationship is one of the forms that the relationship can take. So the data points tend to on the scatter plot tend to cluster around a straight line. That is considered a linear relationship. We just talked about this in the scatter plot example. If it's positive, each time x increases, y also increases. For a linear relationship, it's going to be by a predictable, consistent amount. So as x increases by 1, the y variable also increases by 1 or 2 or 3 or whatever, but it's consistent each time. It is a predictable amount. And that's what makes it a line. And that's what makes it form that linear looking design of the dots. The type of correlation mathematically is called a Pearson correlation. And that's the coefficient that I was talking about, that number. And it describes and measures linear relationships when both variables are numerical scores from interval or ratio scales. So again, we're talking about numerical scores here. To give you a visual example of this, you see these are linear, and you can say monotonic or monotonic. There's different, you'll hear it pronounced different ways, but the graph on the right, the graph on the left, A, is a linear relationship. Obviously, that's a straight line. The one on the right, B, is a monotonic relationship, It is, you can see it's more of a curved line. We'll talk about that in a second. But for A here, this straight line, notice that this is what we're talking about when we say the change is consistent. So as we move across the x-axis, as we move from left to right, the dots increase on the y-axis. They go up. And you can see these don't perfectly line up with the line. That's going to be very rare in behavioral research. But it does generally form that line, right? The change is consistent. And by the way, this is figure 12.2 in your book. So over here on the right, this B, this graph B, this scatter plot B, is the monotonic relationship. Now, this is when it is not consistent, when the change is not a consistent amount. And so sometimes, like here at the beginning, at the x-axis, it's going, the y increase is large as you move across. It jumps very much. It goes very high as you move very little on the x-axis. It goes way up. But then as you progress across the x-axis, it doesn't increase as much. It kind of levels off, right? So an example here is practice and performance. So when you first start practicing something, your performance is going to increase dramatically, right? So the x-axis would be your practice, the amount of practice. Your y-axis, your y variable, would be performance. And so as you progress and you're practicing, As you practice more and more and more and move to the right on the x-axis, you see it levels off because eventually, yes, you're still getting better. Your performance is still getting better, but the big jumps in performance aren't going to be there because you are reaching the point where you are mastering that skill, right? So this is a little bit different. It's not a straight line. So the correlation coefficient or calculation that would be used here is called a Spearman correlation coefficient. And there's more about these correlation coefficients in chapter 15 if you want to know more. But I'm just going to touch on that for now. So that's what we talk about when we mean form, whether it's linear or some other kind of relationship. So the third characteristic of the correlation coefficient is the consistency or strength of the relationship. So how strongly the variables are related to each other, how much one change in one variable, how much that other variable moves with it, okay, as they change. So again, the correlation coefficient measures and describes the relationship between the two variables, right? This is just the review here. The sign that I was just talking about, positive or negative, indicates the direction of the relationship. So again, do they move together, increase together, or does one increase and the other decreases? So that's what that positive or negative is indicating. In a scatter plot, it's showing you which way the line tilts. Does it tilt, up, or does it tilt down? That the second point here is that well, hold on, let me back up. The third point, let me skip down to the last point here. That's what we just talked about, is the form. The Pearson is the linear relationship. The Spearman is the monotonic relationship. And there's other relationships as well, curvilinear and things like that. But that gets into a lot more complicated statistics. But just as far as the form goes, we're really just talking about whether it's linear or not. And that's indicated by those scatter plots or the type of correlation coefficient you calculate. Pearson is going to be that linear relationship. Now, this second bullet point here is the numerical value, whether it's a 0 all the way to a 1. So 0 or 0.25 or 0.7 or 1. That indicates the strength or the consistency of the relationship. So what this means is that a value of 0 is the weakest possible relationship. That means there really is no correlation, no relationship, or no linear relationship there. And so those dots are really just going to be scattered randomly. We'll show you a visual example of this in a second. If it's closer to 0, it's going to be a weaker relationship. The higher it goes, especially once you pass 0.5, you're getting into a stronger relationship. 1 is obviously the strongest relationship. A correlation cannot go above 1. I'm going to say that again. A correlation cannot go above 1. 1 indicates a perfect relationship, which rarely ever happens in behavioral research because behavioral varies so wildly, right? And people are so different. In correlations of things that aren't behavioral related, in what they call more of the hard sciences, you can get perfect correlations between things. But getting something very close to 1 or at a 1 in behavioral research is very rare. So another thing I want to point out here is that because of this, what this means is that if you had a correlation coefficient of 0.8, you also had a correlation coefficient of negative 0.8. Those are the same strength. Those are both very strong relationships. A lot of times that negative symbol throws people off and makes them think that it's a weak relationship. It is not. 0.8 means it's close to 1. That is a very, very strong relationship. The only thing that negative sign is telling you is that it is a negative relationship, meaning the direction. So what that means is as one variable increases, the other is decreasing, but they are very strongly related in that sense. They are moving together consistently. So that I just wanted to point that out to you guys because that can throw people off. So this will help illuminate that a little bit more because here's some examples of different scatter plots here. So this is figure 12.3 in your book. And this first one, the letter A, scatter plot A, this is a correlation coefficient of 0.9. So this is a very, very strong relationship, first of all. You can see it, actually. It looks like a line. It's very close to a line. Those dots are clustered around that 9 very tightly. Around that line very tightly. So this would be considered a strong, positive, linear relationship. So there's your 3 characteristics right there. So when we ask what are the characteristics of a correlation coefficient, or when someone asks you to describe a correlational relationship, that's the 3 things you need to say. Is it strong or is it weak or moderate? This one's strong. Is it positive or negative? This one's positive. And what form does it take? It's linear. So this is a strong, positive, linear relationship. Okay? And again, it's positive because the line is moving uphill as the X increases, so does the Y. All right, graph B, scatter plot B, is a very weak relationship, okay? You can see there is a slight trend in a negative direction. If you drew a line through the middle of this circle, the big circle, you would see they're slightly clustered around a negative line going from the top of Y to the bottom all the way out to the X. Because, and again, that negative means that as the X increases, the Y is decreasing. So it's the opposite direction of graph A. This correlation coefficient would likely be around 0.3 or 0.4. It is a relatively weak correlation. The dots aren't clustered tightly around a line. They are spread out more. So it is a weaker relationship. So you would say that this is a weak, negative, slightly linear relationship. Okay. Graph C is showing you what a perfect linear relationship looks like. That is a -1. The correlation coefficient here calculated would be -1. So this is what it looks like. Now, notice, even though it's negative, it's that negative direction, it is a very, very strong relationship. Those dots are literally right on the line. So this is the strongest relationship possible, but it is a -1 because of the direction, not because of the strength. And again, this is not realistic for behavioral data, so just keep that in mind. Now, this last graph, D, would be a correlation coefficient of 0. There's no correlation. There is no linear trend here whatsoever. They are randomly scattered throughout the graph, no trend whatsoever, okay? So that just gives you an example visually of that. So we talked about numerical scores. What if there are non-numerical scores, okay? So example, what if you're studying whether or not someone graduated from college, how that is related to something. So they're either a college grad or not a college grad. That's not a numerical score. That's just college grad or not college grad. Or maybe, or in the example they use, the other variable that they studied was a problem-solving task. But it's not a score on a problem-solving task. It is whether they succeed in solving the problem or they fail at solving the problem. So it's literally either succeed or fail, pass or fail, right? There's no score. So if there's no numerical score, how do we evaluate a correlation? If one of the scores is numerical and the other is not, you can use, one of your options is to use the non-numerical variable, so the college grad and the non-college grad, to organize the scores into separate groups. So you can have a college group, a college grad group, and a non-college grad group. And we can compare the two groups on their on whatever we want to compare, GPA, whatever, some sort of numerical score. If you do that, you can see that if you're thinking, wait, if we're separating into groups, doesn't that mean it's not correlational anymore? You would be right. This will become a non-experimental study. It would no longer be correlational if we separate them into groups. And you would use a t-test or an ANOVA to analyze it statistically. You would no longer be able to use a correlation coefficient. Your other option, if you want to stick with the correlation, is the second dash point down here that says you can assign a numerical code to your variable. So you could say that the college grads could be 1 and the non-college grads could be 0, or vice versa. It doesn't matter. But one of those categories would be 0, one would be 1. Then you can actually calculate a Pearson correlation coefficient, and it becomes what's called a point biserial correlation. And that biserial obviously is referring to the 0 and the 1 coding. And so you can do that, but the downside to this is that the only thing this will tell you is the strength of the relationship. So that numerical number that you get, that calculation, will tell you the strength of the relationship between the two variables. But the sign, so whether it's positive or negative, or the form, any kind of linear or not, is meaningless. You can't actually use those characteristics or descriptives for this kind of correlation, because the 0 and the 1 code is arbitrarily assigned. It is not a true score. So you can't evaluate it the same way. So that's the downside to that. Now, what if both variables are non-numerical? So we don't have either one being numerical. So the example they gave, like I said, is college grad and no college grad, and then pass or fail. So neither one of those are numerical. How do we do that? Well, you can evaluate it into a matrix, which you've seen these matrices before, where we have college grad and no college and succeed and fail. The difference is these numbers here are not scores. They are the participants, right? So there's 17 college graduates who succeeded in the problem solving task. There's 3 college graduates who failed. There's 12 people that did not graduate college who succeeded in the problem solving task, and there's 8 people who did not graduate college who failed the problem solving task. Okay, so how do we analyze this statistically? You would do a chi-square test, which there's more information about chi-square tests in chapter 15, but just know that's the name of the test you would use to evaluate whether there is a significant relationship here. This, by the way, this is figure 12.4 from your chapter as well. Now, if you don't want to do the chi-square and you want to actually have a Pearson correlation, again, you can code both variables this time instead of just one. You can code them both. So college graduate would get a 1 and no college would get a 0 or a 2 or whatever. And then succeed would get a 1 and fail would get a 2 or a 0 or whatever. And you would do the Pearson correlation, but then it would be known what your resulting calculation would be known as what's called a phi coefficient. And again, only the strength, the numerical value, would be able to be determined and be meaningful to you. The sign or the direction and the form or linearity would not be meaningful at all in this because those numbers are assigned arbitrarily. They're just codes, right? So just things to keep in mind if you see these in research articles, and if you're doing research. This is why a lot of times a lot of researchers prefer to have numerical values to get some sort of score when doing correlations, if possible. Obviously, sometimes that's not always possible, but if it is, it would be preferred. So we talked about, describing the relationship and giving it a correlation coefficient, but what about interpreting it, and what about statistical significance? So for interpreting a correlation, you would use what is called a coefficient of determination. It's just taking the correlation coefficient and squaring it. So Pearson correlation coefficient is usually it is an R. That's that R letter, that little lowercase r. That is a Pearson correlation. So when I was saying a correlation of 1 or a correlation of 0.8, that is the R value. Okay. So down here in this chart, it is showing you that don't look at the correlation. The coefficient of determination yet. Let's just look at this, at the correlations first. So this is showing you that what is considered, these are guidelines for how to determine what is small, what is medium, what is a large correlation. So a correlation of 0.1 or lower is going to be considered a small correlation coefficient and a fairly weak relationship. Here in the medium category, we get 0.3. So if it's between 0.1 and 0.3, generally we would say it is a medium relationship, a medium correlation coefficient, or a moderate relationship between the two variables. And then you see, if we're talking about 0.5, and actually, let me rephrase this. Anything around a 0.3 is going to be considered medium. The way that this is written is a little bit confusing, because what if it's between 0.3 and 0.5? I would still say that is considered medium. These really should be considered cutoffs at the high end. But again, these are just general guidelines, just to kind of give you an example. So anything larger than 0.5 obviously is going to be a very strong relationship. It is a large correlation coefficient. In some of the harder sciences, or things that aren't behavior related, they're gonna want those numbers to be higher to be considered strong. They're gonna want it to be closer to 1. The reason that 0.5 is considered strong here is because, again, behavior in individuals vary so wildly that if you are actually able to get a correlation coefficient of 0.5, that's impressive. That means there is definitely some kind of relationship going on there. So just something to think about. Also to keep in mind is that when we're talking about reliability of measurements or tools, because remember, you can use a correlation coefficient to establish reliability between a tool and another tool, or some kind of measurement and another measurement. Those you want to be as close to 1 as possible. So you would want those to be higher. So this guideline, this chart, is really only for those behavioral variables. So just, that's something to keep in mind. You want to look up the guidelines for the specific things that you're studying when it comes to this kind of thing. This is just a general guideline. Now, the coefficient of determination is the percentage of the variability in one variable that is determined or predicted by its relationship with the other variable. What does that mean? Okay. If you look at our small relationship here in this chart, the correlation coefficient, the Pearson R, is 0.1. If we square that, you see the R squared there, that equals 0.01. So what that means is, with a correlation coefficient of 0.1, we can say that 1% of the variability in one of the variables can be predicted by its relationship with the other variable. Okay. And then with the coefficient of 0.3, then the determination is 9%. So 9% of the variability or the change in one variable can be predicted by its relationship with the other variable. In a real example, a real world example, if we were looking at GPA and IQ, let's say we got a correlation. We looked at college students, we looked at their GPA and their IQ, and we got a correlation coefficient of 0.8. Well, wow, that's very large. It's very strong. The coefficient of determination would be 0.64 because we squared it. If you square 0.8, you get 0.64. So R squared would be 0.64. That's 64%. So we would say that 64% of the difference in GPA, the changes, the variation in GPA, can be predicted by the differences in the IQ variable. Okay. So that is what the coefficient of determination is telling you. It's basically another way of showing you how closely related those variables are, how much they move and change together, right? And the larger that is, obviously, the larger, the stronger the relationship is. The other way to evaluate a correlation is statistical significance. What that means is if a correlation is statistically significant, then we're saying it's unlikely to have been produced or to have happened by random variation or by chance. So, in other words, it's telling you that there is a real relationship there. It's not just the changes didn't just happen by chance. So, within a small sample size, it is possible to obtain a very strong correlation when there actually might not be a relationship at all. And your book shows the example of if there's only 2 participants, there's only 2 data points. Well, of course, it's going to look like a line because there's only 2 points. You could draw a line between 2 points every time. So it's going to look like a strong correlation. But if you got more participants and got more data points, it could end up being very, very scattered and not actually have a relationship at all. So increasing the sample size makes it more likely that if you actually obtain a correlation coefficient, that represents a real relationship if there's a large enough sample size. And there's ways to determine the appropriate sample size for things. And we'll get into that in other chapters. But just know that if you increase the sample size or if the sample size is too small, that can hinder your ability to determine whether or not there's a real relationship there. Another thing to keep in mind is that when you say a correlation is statistically significant, that does not mean that it is a large or a strong correlation. It just means that it's real, that it's not due to chance. So you can have a weak correlation of 0.2 or 0.1 that is statistically significant. All that tells you is that there is a real relationship there. It didn't happen due to chance. There really is a correlation there. But it is a weak correlation, which means that they do move together. The 2 variables do change and move together, just not very consistently and not in a strong way. Okay. Another way to look at it would be to say, as one variable increases, it is somewhat likely that the other variable will increase as well, or decrease, or whatever, depending on the direction of the relationship. But if it's a strong relationship, you would say, as one variable increases, it is very likely that the other variable will also increase or decrease. Okay. Here's a discussion activity. Screenshot this, go through this. It's getting you to think about how this is useful in the real world. That first question, what is the value of a strong correlational relationship? In a clinical example, knowing what variables are strongly correlated or strongly related to self-esteem or anxiety or depression, that can be very useful because then you know to pay attention to those variables in your therapy or in your clinical approach to the patient. Um, and you can use strategies to increase or decrease those variables, the presence of those variables, because you know that that will also help increase or decrease the self-esteem or the anxiety of the patient accordingly. Um, and another example of this last question, the statistical significance, playing, how does that, how could that influence a client? If you explain that to them and that the statistical significance means that it's a real relationship, that it didn't just happen by chance, that may help them understand that what they're going through is not random, that there is really a relationship there, and that those two variables are related to each other. And so again, increasing or decreasing one of those variables can help increase or decrease the other variable, possibly. So that is just an example from a clinical point of view. Here's your learning check really quickly. A college professor reports that students who finish exams early tend to get better grades than students who hold on to exams until the last possible moment because they second guess themselves, I'm sure. The correlation between exam score and amount of time spent on the exam is an example of. Okay, so whenever you're presented with something like this, you got to think this through. So we're saying exam score and the amount of time spent on the exam. So they just said the amount of time spent on the exam, as it increases, as they hold on to that test longer, the exam score decreases. So as the amount of time increases, the exam score decreases. So those are opposites. So that would mean a negative correlation. As one goes up, the other goes down. So again, you got to think it through. You got to pay attention to the wording, because if they had said the amount of time, well, yeah, I mean, yeah, if they had worded that to where they were saying that the amount of time that they or how quickly, rather, let me back that up, how quickly they turned in their test, that throws you off, because it makes it sound like you're talking about turning it in quicker. Sounds like an increase, or a decrease. And so you have to make sure that you're making sure that you pay attention to the wording of it, and actually thinking through it in terms of a data and score perspective. So again, the amount of time on the exam goes up, and the exam score goes down. So just wanted to, I probably confused you because I just confused myself, but thinking through wording can be tricky sometimes, and I want to make sure that you guys know that you need to pay attention to that. Question 2, a researcher reports that there's no consistent relationship between grade point average and the number of hours spent studying for college students. So there's no consistent relationship. So which one of these is the best description for a correlation between those two variables? Well, they just said there's no consistent relationship. So that would mean that it would be near 0, right? Because 0 means there's no relationship whatsoever. If it was a strong relationship, it would be a correlation near 1. And also, just to clarify, again, because there's no consistent relationship, you can't determine positive or negative anyway. But they don't give you any information about how they are moving how the variables are moving, so you wouldn't be able to determine positive or negative correlation from that anyway. What is measured by the Pearson correlation? Hopefully you guys remember that Pearson is for a linear relationship. Okay, so when you see Pearson, automatically associate that in your brain with linear relationship. Okay, so that is it for section 12.2. And if you guys have any questions, I'm here.